Hello, my name is Hannah Elkins, and my project will be the assessment of percent acidity in Coke Zero and Starry Lemon Lime Soda using KHP to standardize NaOH. In this experiment, I analyzed two analytes, which were phosphoric acid as H3PO4 and citric acid as C6H8O7. Citric acid was in the Starry Lemon Lime, and phosphoric acid was in the Coke Zero. I chose these specific acids because phosphoric acid and citric acids are the primary acids in their respective sodas, and they would make up a good portion of the percent acidity. It is important to analyze these two acids in sodas because phosphoric acid and citric acids in sodas largely contribute to enamel erosion and cause erosive tooth wear, which is helpful in dental health. For the literature values, one study found the pH of almost every soda, dark and light sodas, and juices, and they found that Coke products and lemon lime sodas were the most acidic and corrosive. Another study determined that the percent acidity of phosphoric acid in Coke Zero was 0.05 to 0.09%, and the literature value of citric acid concentration in lemon lime soda was 0.03 to 0.22 grams per ounces, and when converted to percent acidity, the value was 0.34 to 0.68%. Two methods that have been used to determine the percent acidity in sodas are potentiometric titration and acid-base titration. Potentiometric titrations titrate sodas with standardized concentration of about 0.1 molar NaOH. While using a calibrated pH electrode to continuously measure the pH, this can then be used to calibrate a potentiometric curve, which you can derive the equivalence point and pKa values from to determine your percent acidity. Acid-base titrations use standardized 0.1 molar NaOH standardized by potassium acid phthalate, or KHP, as the primary standard. For the titration with soda, your titrant would be the NaOH, and then your analyte would be the soda with about 50 milliliters of water and 3 drops of phenolphthalein indicator. The base will then be added to the acid until a color change is detected, which is pink with the phenolphthalein, and the volume of the NaOH dispensed and the balanced equations of the components can then be used to calculate the percent acidity. I chose to do an acid-base titration because I was more familiar with the procedure after doing many similar procedures throughout this semester. Phosphoric acid and citric acid are both triprotic acids, and their first dissociation will readily react with the hydroxide ions in NaOH, creating a 1-to-1 reaction ratio. So here in this first image, we have the dissociation of phosphoric acid and citric acid in water, and then we have the next slide that will show the reactions that will occur between KHP and NaOH, NaOH and phosphoric acid, and NaOH and citric acid in 1-to-1 ratios. For week 1, first, a standardization of pre-prepared 0.1 molar NaOH was used, and it was standardized by the primary standard KHP, which was also pre-prepared. 0.4 grams of the KHP was measured by finding the difference using analytical balances and using a top loading balance for the actual transfer of the solid. The solid was weighed into 3 clean, dry Erlenmeyer flasks that were 250 milliliters. And 50 milliliters of deionized water was added to each flask, as well as 3 drops of phenolphthalein indicator. Paraffin was covered on the flask to swirl it until the KHP dissolved, and then the solution was titrated with the NaOH until a color change of pink was observed for about 30 seconds. The final and initial volume of the Barrett readings were then recorded to later be used for calculations. Then for the Coke Zero titration, 100 milliliters of Coke Zero was poured into a 100 milliliter beaker and stirred with glass stirring rod for about 10 to 15 minutes, as seen in this picture, to remove the CO2. A clean volumetric pipette was then used to dispense 10.00 milliliters of Coke Zero into 5 dry, clean 250 milliliter Erlenmeyer flasks, and then 50 milliliters of deionized water is added, 3 drops of phenolphthalein indicator, and then the solution was titrated until a light pink color was observed, and then the volumes of initial and final volume were also recorded for this. In week 2, one standardization titration was performed as similar to week 1. The Coke Zero was similarly degassed, as well as the Starry Lemon Lime Soda, as again seen in the picture. Titrations of both sodas were performed, but instead of 10.00 milliliters, 30.00 milliliters was taken with a volumetric pipette added to 250 milliliter Erlenmeyer flask, added with 50 milliliters of deionized water, 3 drops of phenyldihydrogen, the same as the previous week, and then the burette readings were recorded similarly. A few problems that arose in week 1 were that the NaOH used to neutralize the 10 milliliter Coke Zero aliquot was less than 6 milliliters, which makes data analysis more difficult to conduct with precision. The Coke Zero in the 10 milliliter aliquot was also difficult to observe the color change. So in week 2, 30 milliliters of the Coke Zero was used, and this produced a volume that was greater than 6 milliliters, so that was good. But then we used 20 milliliters of deionized water and then had to add 30 more milliliters because the color change was again hard to see. So then the Starry Lemon Lime soda comes in. This is a clear soda where you can observe the color change better, but there's no phosphoric acid in Starry Lemon Lime soda, so instead the primary acid is citric acid, which was used in the data calculations. For the results, the average 0.1 molar NaOH concentration from the standardization was found to be 0.09890 plus or minus 0.00014 molar. In week 2, it was 0.09899, and averaged over both weeks, it was 0.09893 plus or minus 0.00013 molar. Percent acidity was then found by using the equivalent weight equation, which is molar mass over the number of ionizable H plus ions, which was 3 in H of citric acid and phosphoric acid, and then the percent acidity equation was used, which is the milliliters of base hydrate times the molarity of base mole times equivalent weight of acid, all divided by the sample volume in milliliters times 10. The average percent phosphoric acid in 10 milliliters of Coke Zero over 5 trials was 0.105 plus or minus 0.06%. In 30 milliliters, n equals 3, it was 0.111 plus or minus 0.001%. And in 30 milliliters of Starry Lemon Lime, it was 0.265 plus or minus 0.012%, and n was equal to 4. The 95 confidence percent intervals for each of the sodas and amounts in the same order were 0.105 plus or minus 0.011%, 0.111 plus 0.1002%, and 0.265 plus or minus 0.023%. As a side note, the average concentration of 0.1 molar NaOH in week 1 was used to calculate the percent acidity of the 10 milliliter Coke Zero, and then the average of week 1 and week 2 of the NaOH standardization was used to calculate the percent acidity for the 30 milliliters of Coke Zero and Starry Lemon Lime. The literature values mentioned earlier were then averaged to determine percent error. Phosphoric acid had a range of 0.05 to 0.09% and had an average of 0.07 plus or minus 0.02%. Citric acid had a range of 0.34 to 0.68% and had an average of 0.51 plus or minus 0.17%. The percent error was then found with the equation percent error equals absolute value of the actual value minus the measured value divided by actual value times 100%. And the percent error of phosphoric acid in the 10 milliliters of Coke Zero was 50%, in 30 milliliters it was 58.57%, and in 30 milliliters of Starry Lemon Lime it was 48.04%. Since these percentages were very high, the upper range of the literature value for phosphoric acid, 0.09%, as seen on this slide, was used to calculate the percent error for the 10 and 30 milliliters of Coke Zero, which were then 16.67% and 23.33%. The lower range of the literature value for citric acid, 0.34%, was then used to calculate the percent acidity for the 30 milliliters of Starry Lemon Lime, which was 22.06%. Here was the color change for the standardization, so you see a light pink color. Here was the standard color change for the Coke Zero, which was like a light golden brown, and it was the same for like the 10 milliliter and the 30 milliliter. And then here's the color change for the Starry Lemon Lime, which is very light pink in that picture. For analysis and discussion for sample calculations to find molarity of NaOH, you took the weight of KHP, divided it by the molar mass of KHP, and then moles KHP is equal to NaOH moles. So then you can take the volume that was titrated and then divide it by 1,000 to get liters, and then you can do moles divided by liters, and that will get you your molarity. And then for the percent acidity, I mentioned the equation before, so you practically just plug the numbers in and make sure you're using the right sample calculations to get your percent acidity. The same thing was applied to the Star Lemon Lime soda. And then to find the percent error, I mentioned the equation already, so again, you plug those numbers in, and I did the percent acidity for percent error of the average literature value and then the lower or upper range depending on the soda, and the errors were very high compared to the literature values. In conclusion, the percent errors, again, of phosphoric acid in Coke Zero and citric acid in Star Lemon Lime were very high. While my measured values and results had fairly good precision, they were not accurate in comparison to the literature value for percent acidity in each soda. This lack of accuracy could have been caused by systematic errors, like reading burette or volumetric pipettes consistently higher or lower than at eye level, which would be precise but lack accuracy. There was also the error from only determining the percent acidity of one acid in sodas, even though titrations of phenolphthalein will measure the total titratable acidity for all acids that donate protons in the range of 8.2 to 10 pH. So it will take more NaOH to neutralize all of the acids, not just the specific acids we are trying to measure. And this would increase the results for percent acidities, which would be a systematic errors if everything would be higher. Since all the results are higher, again, this is systematic error. To solve this, you could use a potentiometric titration like I mentioned before that could provide more accurate results. There could also be random error if you're reading the burette or volumetric pipettes randomly above or below eye level without any order. That would lead to probably poor accuracy and poor precision. And then there could be blunder if you forget to degas the soda. That will lead to high percent acidity. And if you over-titrate your standardization or sodas by 2 to 3 milliliters, that would also lead to blunder and you would lack precision and accuracy. To improve this method, it may be useful to use bromothymol blue, which is a bluish-green color change, over phenolphtalene's light pink color. It also may be helpful to boil the soda for about 10 minutes and let cool to room temperature so you ensure CO2 is removed. I believe that with a different indicator and color change and the ensurement of removal of CO2 by boiling the soda, that my results would have been more precise and accurate and match the literature data more with less percent error. And these are my sources. Thank you.
Any questions?